We've already learned quite a bit about solutions so far in class, but let's do a quick review as we start getting into our next section. So in a solution, we're generally talking about something that is dissolved in water, and we would call that aqueous. Of course, we have other things that we can dissolve in too, but this is our most common one. And so in this system, water is the solvent. And the solvent is what's doing the dissolving. It's the majority component. So then the stuff we put in to the solution that we then are going to dissolve is our solute. And it's the minority component. So if we think about making a solution with table salt, sodium chloride, I'm picking this one because it's familiar. So if you put some salt, some table salt into some water because you're going to cook up some pasta or something, and so you dissolve the salt in the water, the table salt is the solute and the water is the solvent. And we know also that because sodium chloride is an ionic compound, that when it dissolves, it is, well, number one, it's a soluble ionic compound, so it's going to dissolve, and we'll call that aqueous. But what's really happening is that we have sodium ions that are being dissolved and chloride ions, and they dissociate from each other in the solution. And what those sodium ions and chloride ions are doing in the solution is that they're hanging out with water molecules. This is the definition of what it means to be dissolved. If you have something that is dissolved, then the solute particles are surrounded by the solvent particles. When the solvent is dissolved. In the case of water, this is called hydration, just like it is when you drink water. Hydration is when particles of water are surrounding those solute particles and we make a solution. So we're not going to talk right now about the specific interactions between the sodium ions and the water, or the chloride ions and the water. That's covered in the previous chapter, and we're going to end up circling back around and talking about it later. But what we can do is we can talk about the strength of the interactions of the ions themselves with each other. Because when they are in their solid form, you have sodium ions hanging out with chloride ions, and they form what's called a crystal lattice. That's a regular arrangement of these ions that are organized in some kind of regular repeating pattern. And it is called a lattice. The interaction between these, of course, is governed by Coulomb's law, which we've looked at before. And the strength of interaction for those ions for each other is going to depend on how large the charges are. So that's the +1 on the sodium and the -1 on the chloride. And also on the distance between them. So when we have a sodium and a chlorine, and they've formed sodium and chloride, we know that these have an interatomic distance that's the sum of the two radii, which we just got finished talking about atom size and ion size. So that should also be a pretty familiar topic. So the closer these charges are, the smaller this distance is going to be, and so the larger this attractive force is still going to be, this energy is going to be. The same is true for larger charges. So if we have larger charges, and if we have smaller distance, then these are going to be associated with a larger Coulombic attraction. And the reverse is also true. If you have particles that are really large, then they're going to have a larger D, and even though they might have larger ion charges, they might end up having a smaller overall Coulombic attraction because those particles are farther away from each other. And this ties in with our solubility rules that we studied a long time ago, right? We were talking about how some ionic compounds dissolve, but others don't. And we've never really talked about why. So this is getting into some of that conversation. And of course, most of the time, explanations like this comes down to energy. The overall energy of the reaction. So let's think about how we would set up this kind of energy calculation in ways that are familiar based on what we've done with energy so far. Right? We just had a balanced chemical equation where we start with a solid and then we dissolve it. So we could use Hess's law, and ultimately we are actually going to use Hess's law. And so just as a quick reminder about how we would use Hess's law, what we do here is we look up those formation enthalpies for sodium chloride in its solid form and sodium chloride in its aqueous form, and then we would figure out the difference between these. So we already have from our book that the amount of energy to form sodium chloride in its solid form is minus 411.2 kilojoules per mole. But we'd have to find this amount of energy somewhere else. And rather than just jumping straight on in and doing the Hess's law right now, I'm actually going to circle back around to this in a little while, because first I want to talk about a different way of looking at how much energy is needed to dissolve the sodium chloride so that we can get a good sense for how much energy is tied up in this crystal lattice here. That would be called the lattice energy. And in our book, we're going to use the capital U for the lattice energy. So in this case, it would be the lattice energy of NaCl. So the way that we're going to do this is we're actually going to do a very specific application of Hess's law. You remember Hess's law, the big idea here is that any path will give us the total energy for the reaction. And that total energy for the reaction will be the same. So we can take any path to get from point A here to point B here. And so in the past, what we've done is we've used our formation enthalpies as that specific path. But since we want to learn a little bit more about what's going on in our crystalline solid, and we have some skills now that that we can use that come from our understanding of atoms. So we've understood that when we ionize an atom, when we go from a sodium metal to a sodium ion, it requires some energy. But when we go from a chlorine atom to a chloride atom, it actually releases energy. That was stuff that we learned in our discussion of ionization energy and electron affinity. So we're going to use a very specific type of Hess's law, as I mentioned, called the Born-Haber cycle. And in the Born-Haber cycle, what we are doing is we're taking the sodium chloride apart into a different kind of, in a different way compared to the formation enthalpy. We're taking it beyond just the formation enthalpy and up into the ions. So let's take a look at how that's going to look. All right, here's our energy chart just as a general purpose. Increasing energy goes up. So what we have normally done is we have said with our formation enthalpy right here, good, we can still see that. We can see that 411.2 kilojoules are released for every mole of sodium chloride that we make. And so that would look kind of like this. If we take our formation equation, we've said that that always starts from a solid of any of the things that would normally be solid in nature, like sodium, and we need stoichiometric amounts of each element in their natural elemental state. So chlorine is a diatomic gas, so we need half of one of those. And we're going to make sodium chloride solid, and that's going to release our formation enthalpy, which will be minus 411.2 kilojoules per mole. And so then we would be able to make sodium chloride as a solid. So this is just our regular formation enthalpy approach, right? Okay. So instead of just doing this, we're going to recognize that, look, if we want to know something about our sodium chloride, we're going to need to know something about what the ion energies are like. And if we're going to do the ions, we need our elements to be in the gaseous form first. So that's our first step. So if we look at our reactants, we have the chlorine already in the gaseous form, but the sodium isn't. I don't think it should be too surprising to you that this is going to take some energy for us to turn this solid into a gas. The great news is we already know what that's called. That's called sublimation. So this would be our sublimation enthalpy for sodium as an element. I guess I don't need to put solid there because it's obvious. So we're going to turn the sodium into a gas by putting in that sublimation enthalpy. We haven't changed the chlorine at all, so we're just going to leave it as is. However, we do need to make a change to the chlorine because this is a diatomic gas, and if we want to just look at chlorine by itself, we need to split it apart, and that's also going to take energy. So this is called a binding energy. We have 1/2 of a chlorine that we're dealing with, so we're going to have 1/2 of a binding energy for the chlorine. And another way of looking at this would just be the bond energy. So binding energy, bond energy, same idea. And that would be in the gaseous form. So this is going to take us a little bit of energy too. Remember, we already had the sodium in the gas form, so I don't need to change that at all. And now I'm going to have chlorine by itself as an individual atom. So the other thing that we need to do to get ready is to form sodium ions and chloride ions. From our discussion last chapter, we know that it takes energy for us to turn sodium into a sodium ion. And the amount of energy is going to be the first ionization energy for sodium. Okay? And that's, again, something we can look up in a table. We haven't changed the chlorine at all, so we'll just go ahead and carry it through onto our diagram. Now I need a little more space. Also, we're going to start coming down here. What you probably also remember is that when we are making chlorine into chloride, that actually released energy. That was our first electron affinity. So let's go ahead and make that into our next part of the diagram. So we have our electron affinity, the first one for chlorine. So now we have successfully made everything into ions. I have gaseous sodium ions and gaseous chloride ions. And now by definition, the amount of energy that is released if we take gaseous sodium ions and gaseous chloride ions and make them into solid sodium chloride, that is exactly how the lattice energy for the sodium chloride is defined. And that was the whole point of why we drew out this entire diagram, was so that we could identify where is the lattice energy on this diagram? What are all of the parts of the energy that are going into this sodium chloride, and how can we think about them? Okay, So depending on what your material is, some materials are going to have a larger lattice energy than others, and these are going to depend on the same kinds of things that the Coulombic attractions are going to. So if we have larger ion charges, then we're probably going to have a larger lattice energy. So you should look up some lattice energies and see how they compare with different compounds. All right, so this exploration of the Born-Haber cycle let us understand what the lattice energy was, but now we're going to go back to our original diagram and our original chemical reaction and think about what we actually want to do here. So our original chemical reaction was sodium chloride dissolving to make sodium ions that are aqueous and chloride ions that are aqueous. So if we think about what's happening here and compare that to our Born-Haber cycle, the parts that are going to affect the resultant energy here are, we're going to have to take our sodium chloride, turn it into ions, that would be going uphill on the lattice energy, and then we're going to hydrate. We're going to go from the gaseous form of the ion of sodium and the gaseous form of the chloride to the aqueous form of those two ions. So this is a new Born-Haber cycle for us to look at. So we just said that in order to get from where we are to where we want to be, we're going to take this solid, we're going to undo the lattice energy. So this is going to be minus U of NaCl, and that's a solid. And this will take us back to sodium ions in the gas form and chloride ions in the gas form. So this, again, we're just using Hess's law in this very specific way called the Born-Haber cycle. So when we hydrate sodium ions that are in the gaseous form or chloride ions that are in the gaseous form, these release energy. Hydration of ions releases energy because the ions are attracted to the solvent particles. So just like before, let's do these one at a time. So it doesn't really matter what order we do them in. We could look up these numbers. So this would be the hydration enthalpy for sodium ion. And this is going to get us sodium now in aqueous form, but we haven't done anything to the chloride yet, so that's still in gaseous form. And now we're going to go and do it again. So we have another hydration enthalpy for the chloride. And now both of these have been hydrated, and of course you did not know, relatively speaking, what these energies were going to be like. So let's double check this. The way that I've drawn it, this would be the enthalpy of the reaction. That my drawing would imply that this is endothermic. So let's actually look up the values and see. So the tables of thermodynamic values here are going to give us some of the information that we need. Remember that when we dissolve sodium chloride and it has fully dissolved like this, we use a subscript AI in the tables of thermodynamic data. So pause the video and go and look up these two formation enthalpy values in that table, which is probably a couple weeks back now. All right, so hopefully you found, I'm just rounding to the first decimal place here for ease, and because this was the value we had earlier from our textbook. Our formation enthalpy for sodium chloride in the solid form is minus 411.2 kilojoules per mole, and in the aqueous form is minus 407.3 kilojoules per mole if I round these to the first decimal place. So Hess's law tells me that I can add up my formation values together, multiplying them by their appropriate stoichiometric coefficients, and that I can get the reaction enthalpy this way. So again, as a review, because sodium chloride is our reactant and it has a stoichiometric coefficient of just 1, we're going to change that to a -1 because it's a reactant and it's being used up. We'll multiply that by its formation enthalpy. And then we'll add the formation enthalpy for the products, which is also just multiplied by a +1, so I'm not going to mention it. So if I work this out, I get a total of 3.9 kilojoules per mole, which is indeed slightly endothermic. It requires a little bit of energy for us to dissolve sodium chloride in water. So, this is why sodium chloride is not a particularly good choice for melting ice in the wintertime, because it actually absorbs energy rather than releasing energy to help melt ice. Now, it also does have other factors that increase melting that we're going to talk about a little bit later in this chapter. But anyway, that's a first look at it. Okay, so we have just calculated the hydration enthalpy. That's what this was. The overall hydration enthalpy, or excuse me, it's not that. This is called the enthalpy of solution. So let's try doing this calculation again, and let's try it for a couple of different compounds. Have you ever dissolved sodium hydroxide that was solid in water? It's sodium hydroxide. I hope you don't have to handle sodium hydroxide that's solid though, because it's pretty dangerous. It can wear away your skin. So these values are also in our tables of thermodynamic data. So let's go ahead and calculate the reaction enthalpy, the enthalpy of solution, to take solid sodium hydroxide to aqueous sodium hydroxide, and also for KCl, potassium chloride, to be dissolved. We didn't have too many different options in our tables of thermodynamic values, and so if we have some other calculations that we're going to do, we're going to need to look them up elsewhere. All right, so pause the video and do these calculations, and let's see what happens. All right, welcome back. I'm just going to work through our numbers for sodium hydroxide here. Hopefully you found that our formation enthalpies were minus 425.6, whatever, we'll just keep all of them, 609 kilojoules per mole from the thermodynamic tables, and minus 470.114 kilojoules per mole for the aqueous. Can you see where this is going? So our enthalpy of reaction here, our reactant gets that -1, and our product gets a +1 multiplied by their reaction enthalpies. So this one I get minus 44.505 kilojoules per mole. Unlike sodium chloride, sodium hydroxide releases quite a bit of energy. And if you're ever making a sodium hydroxide solution, this also will work if you take a more concentrated solution and you dissolve it, you dilute it, you will probably feel that the reaction vessel feels warm. So just be aware of that. It does release quite a bit of energy. However, for the potassium chloride, if you worked those numbers out, then you should also have found that this one, like the sodium chloride, is also endothermic. So the two pieces that I want you to be comfortable with from this part of the reaction is being able to build and do calculations with the Born-Haber cycle. So I have a couple of practice problems in there for your smart work. And then the second part of this is just being able to do these enthalpies of reaction from our formation enthalpies. And this is hopefully a nice review of that previous section.